Imagine you are a NASA engineer. You have spent 15 years on this project. You know every bolt, every circuit, every thermal rating. You have run the numbers hundreds of times, and the numbers tell you something you do not want to hear. The heat shield, the single piece of hardware standing between 4 astronauts and 4,000-degree plasma, did not behave the way your models said it would. After the uncrewed Artemis I test flight, inspectors found uneven erosion, unexpected cracks, and missing chunks of the ablative material. The capsule came home in one piece, but it came home differently than you predicted. Now the crewed mission, Artemis II, is on the pad. 4 humans, a lunar flyby. No rescue plan, no lifeboat, no ISS to dock with if something goes wrong. And you are being asked whether the gap between what your models predicted and what actually happened is acceptable. That exact question, has been asked before at NASA. The answers given have not always been the right ones. Welcome to History Repeating. I am your host, and today we are doing what this channel was built to do. Place a current technical moment inside the longer institutional story that produced it. Because the Artemis II heat shield problem is not just an engineering problem, it is a pattern problem, and the pattern has a track record. Part 1. What the Artemis heat shield problem actually is. Before we go anywhere in time, let us be precise about what we are talking about. The Orion capsule's heat shield uses a material called Avcoat, an ablative shield designed to literally burn away during reentry, carrying heat with it rather than letting it penetrate the capsule structure. After Artemis I, engineers found that the Avcoat had eroded unevenly, charred deeper than predicted, cracked in unexpected ways, and in some places disappeared entirely. Let's be clear, the heat shield did not fail. The capsule came home. But that is not the point. The point is the gap. In spaceflight, the gap between what your models predict and what actually happens is exactly where danger lives. And the gap matters especially here because returning from the moon is categorically more violent than returning from the International Space Station. A capsule from low Earth orbit hits the atmosphere at around 28,000 kilometers per hour. From the moon, it is nearly 40,000. Heat generation does not scale linearly with speed. It scales exponentially. That extra velocity creates a thermal load orders of magnitude higher. The heat shield is not just working harder, it is working in a different regime entirely. To manage that energy, Orion performs what engineers call a skip reentry, dipping into the atmosphere, using its own shape to generate lift, bouncing back into space briefly, then plunging back in for the final descent. Beautiful in theory, demanding in practice, and it requires the heat shield to perform precisely as predicted at every stage of that maneuver. The unquantified risk is not that the shield might fail in a known way, it is that it might fail in a way that cannot be modeled. A hotspot, a plasma intrusion, a structural breach the engineers cannot calculate for because they do not fully understand why it happened the first time. That is the situation. Now let us put it in context. Part 2. The pattern, Apollo 1, Challenger, Columbia. NASA's worst disasters do not share a root cause of technical failure. They share a root cause of institutional decision-making under pressure in the presence of known warnings. Before the Apollo 1 fire, in 1967, engineers had flagged serious concerns about the pure oxygen cabin atmosphere and the flammability of materials inside the command module. The warnings were documented. The schedule pressure was intense. The fire killed Gus Grissom, Ed White, and Roger Chaffee on the launch pad. Before Challenger in 1986, engineers at Morton Thiokol sent a memo recommending against launching in cold temperatures. The O-rings in the solid rocket boosters had shown concerning behavior in cold weather tests. Management overruled them. The temperature on launch morning was 29 degrees Fahrenheit. Challenger broke apart 73 seconds after liftoff, killing all 7 crew members. Before Columbia in 2003, engineers knew that foam from the external tank could strike the heat shield during ascent. It had happened on previous missions. The risk had been normalized. A foam strike during launch damaged the leading edge of Columbia's left wing. On re-entry, superheated plasma entered through that breach. Columbia disintegrated over Texas and Louisiana. 7 crew members died. The pattern is not that these disasters were unforeseeable. It is that they were foreseen, and the decision was made to fly anyway. Each time, the pressure came from the same sources: geopolitics, budget cycles, program momentum, and the accumulated inertia of a massive industrial ecosystem that could not simply pause. Artemis II is facing the same cocktail. The United States is in a strategic competition with China's lunar program. The Artemis program has cost tens of billions of dollars and depends on congressional confidence for continued funding. Thousands of contractors and suppliers are tied to the program's schedule. A major delay does not just delay a mission. It threatens to freeze the entire economic engine. Those are not trivial pressures. They are the same pressures that existed in January 1986 and February 2003. History asks us to notice that. Part 3. The crucial difference: unknown unknowns versus known unquantified risks. It is tempting to compare Artemis II to Apollo 8, the first crewed lunar orbit in December 1968. A mission assembled in months, launched with an audacity that still seems almost incomprehensible in retrospect. But the comparison obscures a critical distinction. Apollo 8's crew accepted what engineers call unknown unknowns, the risks inherent in going somewhere no human had gone before, risks that could not be modeled because there was no prior data. That is brave. That is exploration. Artemis II is facing a known unquantified risk. Engineers know the heat shield behaved unexpectedly. They know where the anomalies occurred. What they do not know is why, with enough precision to say with confidence that it will not happen again, or happen worse, on a crewed flight. That is a different category of risk. Known unknowns are the ones that have historically preceded NASA's worst days. The O-ring engineers knew the rings were a concern. The foam engineers knew foam strikes happened. The Artemis engineers know the heat shield surprised them. The question, always, is whether the gap between what is known and what is understood is acceptable, and who is making that judgment, and under what pressures. Closing. History does not repeat, but it rhymes. NASA is not the villain of this story. It is an institution doing something genuinely difficult, returning humans to the moon for the first time in 50 years, with technology more complex than anything that came before, under pressures that would bend any organization. And NASA has also learned from its disasters. The post-Columbia reforms changed safety culture in ways that were real and documented. The people working on Artemis are not the people who normalized foam strikes in 2003. They are people who know that history and are trying not to repeat it. But institutions carry patterns that outlast the people inside them. The pressure to fly, from geopolitics, from budgets, from the sheer gravitational pull of a program in motion, is structural. It does not require anyone to be reckless. It just requires everyone to find the known risk acceptable enough. One more time. The Artemis II heat shield problem is not the Challenger O-rings. It is not Columbia's foam. Each of those moments was specific to its time, shaped by its technology and its politics. But Artemis II rhymes with both of them. It rhymes in its structure: a known anomaly, an unquantified risk, a crewed mission on the schedule. It rhymes in its pressures: the geopolitical race, the budget cycle, the industrial ecosystem that cannot easily pause. And it rhymes in its question: is the gap between what we predicted and what happened acceptable when 4 human lives depend on the answer being right? History does not tell us the answer. It tells us to take the question seriously. This is history repeating. If this raised questions you want to pursue, start with Richard Feynman's personal appendix to the Rogers Commission report on Challenger, one of the clearest documents ever written about institutional risk tolerance in engineering. And look up the Columbia Accident Investigation Board report, which remains the most thorough post-mortem on organizational safety culture ever produced by a government agency. If you found this useful, share it. Not for the algorithm, because this kind of thinking needs to travel. Subscribe if you want to keep doing this kind of work together. Leave a comment and tell me what history you want to examine next. The past is not finished. It is working. And so are we.